I want to share with you some recent understandings on the time periodic solution for a kinetic Fokker-Planck equation for neural networks. This is a joint work with Jose Carrillo, who's in the audience, and Zhou, who's my PhD student in his first year. And this is advertisement time. Those are pictures of our center, Beijing International Center for Mathematical Research. Benoit has been there, but I guess for most of you have not been there yet. Please do visit us, maybe after this pandemic. And this is the outline of today's talk. I reckon that some of you are not very familiar with the voltage conductance model, which is the focus today. So I will still spend quite a few slides presenting this model and the current knowings. And I would like to show you our current understanding from two aspects. And so let's get started. So today we want to look at neurons whose structure is very, very complicated, okay, which is shown on the left bottom picture. But we are interested in the time evolution of the membrane potential or the voltage. So the evolution of the voltage, has many mechanisms in it. So let me break it down and show them to you one by one. So the first thing is a leak. So whenever there's no external signal or influence from the network, the voltage will quickly equilibrate to its relaxing value, denoted by V naught. And the second mechanism is firing and resetting. So whenever the voltage reaches the firing voltage, which is denoted by VF, it will immediately form a spike and jump to a lower value, which we call it the reset voltage, denoted by VR, as is shown by those like peaks here. Okay, and the last part might be the most important part. Well, I want to account for the influence from the network, because we do not just want to consider independent neurons. And within a large neural network, the neurons can form spikes to influence other neurons. Okay, and there are so many ways to model this average effect. However, no matter how you model it, you have to have in some sense, a mean field description so that you can do analysis. Otherwise, it can be too complicated. So in other words, from the perspective of PDE, we're seeking a statistical description of the neural network. There, we should at least have a neuron density denoted by rho of TV and the mean firing rate. So the neuron density means, given a time, the probability of finding a neuron at a specific voltage, and the firing rate accounts for within infinitesimal time how many neurons has fired, okay, within this short time. Okay, and people already have derived a lot of models for the neuron density with only voltage is considered, and by numerical simulations we can actually observe a lot of periodic solutions. But direct analysis for time periodic solutions has always been a very, very challenging thing. So for inhibitor neural networks, I think the next talk will be related to it. And Pierre, who's I think sitting in the audience, has some recent result on it too. However, for excitatory neurons, although there are some results from the probability side. Professor Tanki is obviously an expert in this. But from the PD side, there's basically very few works. Okay, and today we want to look at the excitatory network, and we want to look at the voltage conductance model. That means we do not just want to consider the evolution, with the voltage is in the game, but also another latent variable that is a conductance. So we use P to denote the Zhou density. Okay, so this P means given time, the probability of finding a neuron with the specific voltage V and conductance G. Okay, but theoretically, if you take the marginal in the V direction, you should be able to recover the density in the V picture. So finally, let me show you the voltage conductance model. So this model has been studied by mathematicians and scientists for like 2 decades. Obviously, I cannot list all the previous results, so let me just mention some pioneering works. So in terms of modeling, we have this Peanuts paper by the Cron group. And for numerical investigation, with bifurcations and the systematics for numerical oscillations, this work by Maria, Jose, and Louis, who's actually my colleague at Peking University. And also for theoretical analysis, Benoit and Delphine have some fundamental result in this KRM paper. Okay, so what is this model? Basically, this model is the evolution for this density within the half-infinite stripe. So V is confined between two values, VR and VF, and the G is positive. So basically, we are considering time evolution within this half-infinite stripe. Okay, and we can view this evolution equation as a generalized conservation law. So in the V direction, we see the flux in the V takes this form. Okay, basically, this is a pure transport term. But if we take a second look at the velocity field, we will find that this is very interesting. Basically, this is a computation of two springs. Okay, one of the spring is driving the potential to the relaxation to VR, and the other spring is driving the potential to VE. So VE is called the excitatory reversal potential, which is slightly bigger than VF. Okay, and for the relaxing spring, we see the strength is a constant, and that GL is referred to as the lead conductance. But the strength of this excitatory spring has a variable strength, which is denoted by just precisely the conductance G. Okay, so obviously there are two possibilities for this computation. For G large enough, we will see this excitation spring will win, and that will drive the voltage eventually passing VF and form a spike. Whenever there's some flux leaking from VF, it will go back to the system to VR. So this mechanism is corresponds to the far end resetting mechanism. Okay, and obviously when G is not so big, in this zone we can observe there's no firing at all. So how do we model the nonlinear inference from the firing? So firstly, let's define the firing rate. Because we see along this line, we may observe some leaking flux. We just can integrate all those leaking flux, and that can give us actually the total firing rate. Okay, and that total firing rate will affect the network in the G direction. Okay, so it's not directly on the V direction, but it first acts on the G direction. So what's in the G direction? The flux in the G direction takes this form. So that should remind you of the Fokker-Planck operator of an OU process. So that means the profile in the G direction is basically a Gaussian. So the preferred conductance is denoted by G in, and A of T is a diffusion parameter. Okay, and that determines the width of the Gaussian. Okay, and in this setting, because we are considering the excitatory network, that means we want to assume this form of G in. So G in is G0 plus G1 times N of T. Okay, so that means whenever there's a firing, the preferred conductance is pushed upward, so that the more neurons have the tendency to fire. Okay, so that gives you a positive feedback. So now we are interested in what happened to this model, and can this model actually give you some periodic solutions? Okay. Finally, in this model, we observe there's epsilon. So epsilon here describes the time scale ratio between the activity in conductance and in V. So let me give you some impressions. Here's a numerical observation. When epsilon is 0, so that means this model can be reduced to a transport equation in V, and surprisingly, you can observe some finite blow up in the firing rate. Okay. So the blow up is happening like around this part, and if you zoom in, we see the peak of the firing rate is going up, and until it just blows up. Okay, so and on the other end, if epsilon is large enough, so here epsilon is 0.002, so we start to observe that the firing rate it has an oscillation, but eventually the magnitude of this oscillation is damped, and will convert to the equilibrium. Okay, so well, at least now we're observing two scenarios. When epsilon equals 0, it's really the transport in the V direction that's dominating the dynamics, and we start to observe the blow up in the firing rate. On the other end, if epsilon is large enough, we start to see the diffusion is dominating, and the whole dynamics is driving to the global equilibrium. That brings up the question: what if we consider a moderately large epsilon? Okay, epsilon is small but still positive. Is it possible to have the balance between the concentration and the dissipation? Well, at least numerically, we can observe this. So let's choose epsilon to be 0.001. So in this case, we start to see the mean firing rate start to show the periodic patterns, okay? And well, now that brings out the question, can we understand this from the PD perspective? It looks like a Hopf bifurcation, which is happening for some positive epsilon zero. Can we really, prove the existence of this Hopf bifurcation and eventually show the existence of the time periodic solutions? Well, the answer is still no so far, but we are moving towards to this direction, okay? So we're having a hard time in analyzing it because the PD structure is so complicated, so that we have to consider some simplified models to understand the role of each part of the PDE. And eventually, I guess we're really getting very closer to understanding the time periodic solution, but still there's the tiny gap, okay? So first, let me present you a toy model. So in the first toy model, we want to make one essential change. That is, we remove the leaking mechanism. Okay. So if we remove the leaking mechanism, it turns out we can show that it's equivalent to we are setting the flux in V just to G times P. Okay. So now the transporting V part, is reducing to the familiar operator in the kinetic equations. It basically means the larger the conductance is, the faster it's driving the voltage to the firing threshold. Okay, and another simplification is only technical. We want to extend the domain for G to R. Okay, so in this case, now we're having a PDE which is still nonlinear. Okay, but now it's defined on the infinite stripe. V is between 0 to 2 pi, and the G is in R. Okay, but one essential observation is that if we remove the leaking mechanism, we can actually do some fun Fourier series analysis to it. So because now everything is periodic in V, so let's try to expand it in the Fourier series, okay? And we can derive the PDE for PM, the coefficient for each mode in the V direction, okay? But let me emphasize here, the PM satisfies a PDE, but it's not actually decoupled from the rest of it. They still have the nonlinear coupling through G in and N of T, and they are coupled through the firing rate. And we're able to prove something, well, kind of expected, but a little bit surprising. That is, okay, no matter what so in spite of nonlinearities, the solution actually will converge to the V homogeneous mode. Okay, that is, if we denote by V0 the V homogeneous mode, the discrepancy between P and P0 will decay exponentially in time. It actually has a very shocking implication. So in spite of the nonlinearity, the V marginal distribution of this joint distribution will only converge to the trivial constant steady state. In other words, we can never see any concentration in the V direction at all. Okay, and with this, what about the fluid dynamics? It turns out we can have a very clear characterization of the long-time behavior of this PDE. So it has two scenarios. So either G1 G1 is essential, the nonlinear parameter. If G1 is too large, say it's bigger than 1, the firing rate will diverge in infinity when T is approaching infinity. Otherwise, the whole solution will become a V homogeneous and then convert to a Gaussian in the G direction. Also, the center and the width of the Gaussian will be driving to the global attractor, such that we can eventually show the solution will be converging to the unique steady state. Okay, so that can be done. Well, we do not have the explicit convergence rate, but we can show this convergence is actually valid. Another implication of this result is this toy model is good in that we understand everything about this long-time behavior, but it becomes boring because it does not really admit time periodic solutions for finite positive epsilon. It only has the time periodic solutions when epsilon is 0. Let me further show you the behavior, by this numerical simulation. So when epsilon is 0, because this model reduced to a very trivial transport equation, and you can easily see that it can admit the time periodic solutions. However, whenever epsilon is finite, no matter how small it is, okay, you start to see the oscillations, but the oscillation will be damped over epsilon time, and will eventually convert to the steady state. Okay, so the lesson we have learned from the analysis of this time model is, surprisingly, the leaking mechanism is very important, because otherwise you cannot really observe interesting time periodic solutions. Okay, so in the second toy model, we just want to add it back. So now in this flux in the v direction, we see the velocity field is again the combination, the computation between the two springs. The one that is driving the voltage to VR, the other one is driving it to fire. Okay, so now the only difference between this model with the original time or the original kinetic model is that we now relax the domain of G to the whole real line. Okay, but the nonlinearity and the non-dependence are still the same. Okay, so we expect that now this toy model should actually have some concentration mechanism in it. But how do we prove it? This is a very hard question because we just do not have the available analysis tool to characterize the concentration. Okay, so eventually this is what we did. We examined the fast conductance limit. We found that the conductance limit has a very interesting behavior. Okay, so now with the leak mechanism adding back, the velocity field is still the combination of two springs, the leak spring and the excitatory spring. But let me remind you, G in has two parts. This G0 part has nothing to do with the firing, but this N1 part, is a coefficient for the firing. So that suggests us we should do another separation. We can separate this G0 part from G in and combine this with the leak spring. Okay, and from this, that means there's another perspective to view the two springs. So now effectively we're having two different springs. The first spring is like this, when there's no firing at all. Okay, the combination of G in and the leak spring is giving something like this. So the combining effect is like it's still driving the potential to something slightly bigger than VF, but now smaller than V capital E. We call it V small e. So we call this the intrinsic drive because in the absence of firing, we still have this drive. Okay. However, whenever there's just maybe a little excitation, if we actually drive it to a larger value with capital E, and we call this the excitation drive. Okay, so it is a difference between this intrinsic drive and excitation drive that can actually count for the concentration. Okay, and how do we prove it? Well, we're having the following observation. So first, we compute the firing rate in terms of the boundary data, and we see that it takes this form. And we observe that because of the denominator, the boundary data, rho TVF, cannot actually exceed a finite number. Because when rho TVF reaches this number, that can make this denominator 0, and the firing rate blows up. Okay. However, due to the difference between the two springs, we can prove that if the solution exists globally, the boundary data will eventually blow up to infinity as t goes to infinity, and that clearly gives a contradiction. Okay, if it exists, we'll just go to infinity. However, it cannot actually exceed this number in order to make the existence. So by this negative argument, we can show that in a very weak sense, the firing rate blows up in finite time, and that's so far that's the only way we can characterize the concentration mechanism. Okay, so finally, let me show you more numerical evidences. We start to see it from the spectrum side. I think my time is running out. Maybe just look at this picture. Okay, so I compute the eigenvalues of the Fokker-Planck operator. We see when epsilon is 0.1, that means in the large enough regime, we see all those eigenvalues except the 0 eigenvalue has negative real part. That means as time goes by, their contribution will decay exponentially in time. However, when epsilon is slightly smaller, say here, when epsilon is 0.085, we start to see some of the eigenvalues start to gain the positive real part. So it's the part of real part that implies instability, and that may account for the Hall bifurcation and may account for the limit cycle. Okay, but we have to admit that so far that's all the story that we can tell, because we are still on the way to give a more complete rigorous proof. And we hope, maybe in the near future, we can give you more stories. And also, I want to emphasize that we still do not have a full understanding of the concentration mechanism and the steady state. because the velocity field in the real problem has, takes a non-separable form. There are so many prevailing, like a coercivity method or some other method, they just can fail very easily. So in order to have a rigorous proof, maybe there's some foundation work to do. That might be understanding each part of the PDE. Okay, with that, I would like to conclude my talk. So embarrassingly, oh, there's another movie for this toy model. Numeric evidence just shows so perfectly, and the curiosity of proving such the existence of those time periodic solutions just won't let go. Okay. Today's talk is based on the two papers we haven't really finished up. I hope they should be out very soon. And with that, I'd like to thank you for your attention.
Thank you, Zhennan, for this very interesting talk. Are there questions by Zoom or YouTube?
Thank you for your presentation. Very interesting. I was wondering, did you compare the frequency of the oscillations to rhythms, to those of the rhythms which are present in the brain, like alpha, beta, gamma, delta? Or can you tune the parameters so that you obtain these rhythms?
Oh, that is a very, very good question, and we should definitely look at it. But so far, those are only theoretical understandings. We haven't do any data assimilation, so those are only for like mathematical parameters, not for scientific inputs.
If I understand well, all the patterns come from the V variable always. And do you think there is a possibility that you would have periodic solutions coming from the other variable, from the conductances, and that the V would not be the driving force?
I think we have thought about it. So I guess if it is like in the inhibitory network, maybe it's like more possible. Yeah, because it's like you're maintaining like a Gaussian profile, but the center of the Gaussian can experience a periodic motion. So in that case, maybe you can prove periodic solutions in the conductance variable. I think at some time we thought about it, but we didn't really go through all those analysis.
We have time for one more question. I have one. It seems to me that for epsilon equal to 0, you have no more diffusion part.
That's right.
Yes. What happens if you add to the nonlinear part a non-zero diffusion coefficient? Do you have the same behavior? Can you observe oscillations?
Oh, well, so actually there's a difference between the original model to the first toy model. So in the original model, if epsilon goes to 0, it will see the concentration and the blow up of the firing rate. But if we consider a different velocity field, like in the first toy model, the zero mode will actually have the periodic solutions. Will no longer have the blow up behavior. I hope that answers your question, or I misunderstood.
Thank you.
Oh, thanks.
Okay, so it's time to turn to the second speaker. We thank Zhennan